Welcome to the CFE Media and Technology Education session, How to Specify Motors for More Efficient HVAC Systems. I'm your moderator, Amara Rozkis, with CFE Media and Technology. For the best experience, here are some tips. This session is set up in a linear progression requiring attendees to view all in-course content before moving on. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. If you'd like to take notes with this session, click on the left panel labeled Notes to do so. Please remember to attend the discussion forum with additional input from industry expert Ken Lavorne. If you are interested in receiving one AIA CES approved learning unit for this event, you need to pass a 10-question exam and get at least 80% correct. In keeping with the American Institute of Architects Continuing Education System Policy, please take some time to read the quality assurance slide. In keeping with our CEP policy, please take some time to read this quality assurance statement. Again, here's some information about obtaining approved PDHs for today's session. Here's an overview of today's session. The presenter will cover this during the technical presentation. And finally, here's a list of the learning objectives. We'll touch on these in today's presentation. Please note that any red, underlined text that you see is a hyperlink to a reference or resource to guide you to more information. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. It's my pleasure to introduce today's speaker. Kenneth Lavorne has more than 30 years of progressive design and engineering management experience with architects and engineers and consulting engineers designing electrical systems. His work designs include single-family and high-rise residential, light industrial facilities, office buildings, institutional facilities, and renovations. He's handled lots of different types of new facilities, including hospitals, K-12 schools, and higher education facilities. It's great to work with you today, Ken. You're live now.
Thank you, Amara. After having designed hundreds of VF drives to replace standard motor starters, I found that it's more than just replacing the motor starter when you add a VF drive to a system. The first issue that you come up with is disruptive voltage wave harmonics, which carry out throughout the system and disrupt the operation of other electronic equipment throughout the facility. If you have a 6-pulse VF drive, you will get 5th and 7th harmonics primarily. If you have a 12-pulse drive, you will primarily have 11th and 13th harmonics. With an 18-pulse drive, which you typically see for larger motors, there will be few harmonics because the harmonics have a tendency to cancel each other out when you have an 18-pulse drive. This whole idea of taking out the VF drive and putting in a standard motor starter is counterintuitive to the standard practice today, because our goal is always to reduce first cost and reduce operating cost. Instead of being able to reduce operating cost by the addition of the VF drive, we're proposing that we can reduce the first cost by not having a VF drive at all, and we can also reduce operating cost by having a fixed speed motor. While adding VF drives is a common practice, the capability of doing this is if you have a system that has a constant volume, no matter what the speed is, and you can start considering replacing the drive with a standard starter. The principles that you use for drive removal are that typically fans are designed for 80% loading or less, and then the motor speed is adjusted to compensate for that using a VF drive. As the motor efficiency drops off from full speed, it gradually gets lower and lower, and so you're having more and more losses as you approach the lower speeds. When you add a VF drive, you have insertion losses, which are also a loss of power. And if you can reduce the static pressure in the ductwork so that you don't require as much horsepower, you can end up saving operating cost. We're going to look at a sample system in which we'll have a 50 horsepower air handling unit. It happens to have an operating point on the fan curve of 39 horsepower. That's too close to 40 horsepower for most typical applications, and most engineers won't specify a 40 horsepower motor for a 39 horsepower operating point. If we want to get our 30,000 CFM constantly, then the typical approach is to put in a 50 horsepower motor and then reduce the speed down with a VF drive. At this operating point, for this particular fan, it requires 6.1 inches of static at water gauge at the operating point. The motor would be operating at 92% efficient. Typically, high efficiency motors operate around 97 or 98%, so you have a drop off in motor efficiency due to it operating at a lower speed. And then the VF drive at this particular point is about 97% efficient. The electrical load for this, by the time you go through all the numbers, turns out to be about 32.6 kilowatts. Okay, the initial cost for the VF drive system for a 50 horsepower motor is $3,358. For the VF drive itself, it's going to be $4,902. And because of the harmonics, a passive harmonic filter to reduce the harmonics to a reasonable level is $2,951. So the total cost is $11,211. And these costs were off of actual motors, drives, and filters that I found on the internet. Okay, if we reduce the static in the duct system from 6.1 inches of static to 3.3 inches of static, we're able to achieve with this same fan the 30,000 CFM with a 25 horsepower motor. At its operating point, it's operating at 24 horsepower. So that's pretty close. The motor is still operating at 92%. The VF drive is still operating at 97%. The 25 horsepower system has cost of $1,979 for the motor. A NEMA combination starter is $1,278 for a total cost of $3,257. As you will note, we didn't have any cost for the harmonic filter because no harmonic filter is required since it's a cross-the-line starter. We could save some money by using a definite purpose starter, but the definite purpose starters are not as robust as the NEMA class starters. And so for our applications right now, I included the NEMA class starter instead of the definite purpose. The fan curve that you see here is for both the 50 horsepower and the 25 horsepower systems. The upper X, if you start at the 30 and go up to just above 6 inches of static pressure, is the operating point for the 50 horsepower motor. And the lower X, there on the same line, that is just about 3.3 inches, is the operating point for the 25 horsepower motor. So we dropped 2.8 inches of static pressure on this fan, and we didn't change anything else. So you ask, how did that happen? Well, that's coming up. Okay, we have a 25 horsepower air handling unit. We have 30,000 CFM constant. It operates at 3.3 inches water gauge. The operating point is 24 horsepower, if you will note from the fan curve. The motor efficiency is 92%. The BF drive efficiency is 97%. The basic system operating cost is based on 12 hours a day, 5 days a week, for 52 weeks out of the year, which is 3,120 hours per year. If your particular system operates more days per week or more hours per day, then obviously it would adjust things upward. And likewise, if it's less hours per day, it would adjust things downward. We're basing our calculations at 12 cents per kilowatt hour, which is pretty low for high concentrations in metropolitan areas. But I think that's 12 cents a kilowatt hour is pretty typical for smaller residential and light industrial, less urban areas. So the 50 horsepower motor, which has a total operating load of 32.6 kW, will run $12,205 per year in electrical cost. The alternative system, which is the 25 horsepower system, we have the same number of hours per year, 3,120. We have the same kilowatt hour cost at 12 cents a kilowatt hour. The 25 horsepower motor operates at 20.3 kW, and it will cost $7,589 a year in electrical cost. Now, to compare this as a real system rather than an individual fan, we're going to assume that we have a 10-story building with 2 systems per floor, so 60,000 CFM per floor. So that will take 20 air handling systems. If you have $11,211 for the installation cost for the 50 horsepower system and 25 horsepower system cost would be $3,257. The cost differential between the two is $7,954. Multiply that by 20 systems and you get $159,080. This is a significant number for savings on the 2 mechanical systems. Now for the operating cost. Again, we have the 20 systems at 2 per floor. The operating cost for the 50 horsepower fans are $12,205 each. The operating cost for the 25 horsepower fans are $7,589 for a cost difference of $4,616. The annual operating savings is, as you can see, $93,320. And we wanted to project this over the life of the system, which is generally considered 20 to 25 years. We selected 20 years for this analysis. Obviously, if it was 25 years, it would be more savings, but the 20 systems will save $1,846,400 over the life of the building, which suddenly becomes more than just chump change. Now, because we've reduced the electrical load in the building, the 50 horsepower motor operates at 65 amps full load. The 25 horsepower motor operates at 34 amps full load, or a difference of 31 amps. You're going to ask, why is it we're using actual full load amps instead of the operating amps? The reason is the electrical system is designed based on full load ampacity. We don't make any reductions for reduced operating ampacity if VF drives are utilized. And so the electrical system is designed based on those full load ampacities. And if you reduce 20 fans at 31 amps apiece, you have a reduction of system ampacity of 620 amps at 480 volts. That in the savings of the distribution equipment, the main distribution panel, the incoming service conductors, the feeders, the branch circuit conductors, and all the other stuff associated with electrical is over $150,000 in initial cost savings. It won't make any changes in the operating cost, but it's still significant for the initial cost savings. Okay, let's say for a moment that you can't get 2.8 inches of reduction in your static pressure. So just in case, we looked at an alternative system. This is the same fan curves, the same X at the 6.1 point on the 30,000 CFM vertical line is the 50 horsepower motor, and the X at the just over 4 inches of static just falls right below the 30 horsepower fan. And so that means that you could operate this with a 30 horsepower fan. That will require that you reduce the total static by to 4.1 inches instead of 3.3. That will give you a 29 horsepower operating point with the same 92% efficient motor and 97% efficient drive. Oh, we have a slide showing all these values written down for you. So okay, the operating system cost for this alternative system, we have the same number of operating hours per year, the same electrical cost. The motor's operating at 24.3 kilowatts, and so the electrical cost annual is $9,108. If we look at the system operating comparison for the 30 horsepower system, we still have the 20 systems. The 50 horsepower operation is still $12,205. We bring our $9,108 per year operating cost for the 30 horsepower system. So now our savings is only $3,097 per system, or an annual savings for the 20 systems of $61,940. However, over the life of the system, we still save $1,238,800. all of these calculations were based on published efficiencies by major manufacturers. All of the data that we're going to be discussing shortly here on static pressure and efficiencies of various ductwork fittings were taken out of the ASHRAE handbook under the chapter Duct Design. There's multiple fittings and there's multiple values throughout this duct design. This is a fairly extensive chapter. We only took 1 point attempting to compare the fittings so that we could compare them apples to apples instead of apples to peanuts. Just so that you know, and we've included this article as one of our supplementary readings. There was an article written several years ago that was published in the Air Movement and Control Association publication, proposing that leaving the VF drives was more efficient than replacing it, as we're proposing here. I attempted to analyze the calculational methods that they used. They didn't have enough data in the article for me to make any determination of exactly how they came to that conclusion. So we're just noting it here for your perusal, and you can read it and see what you decide. Okay, the first thing we're going to talk about on reduction of static pressure in ductwork is, instead of using 90-degree turns, you would use radius turns, or if you do have a square turn, you can put in turning vanes within the turn on the ductwork. The second methodology that reduces the overall static pressure in a duct system is you can oversize the ductwork so that you're carrying the same amount of air. It goes at a lower velocity, and so therefore less friction. You have less static pressure losses. The next one is you reduce the duct aspect ratio. We'll get into a little bit more about the definitions of that, but in essence, you use ducts that are either round or square, or at least close to square. If you start getting into ducts that are real wide and fairly short, that gives you a high aspect ratio and reduces the, or increases the losses, increases the static pressure. And then the last item is the discrete use of dampers. We're going to look at some dampers, and you're going to find that dampers have incredible losses in a duct system. So you need to be very, very careful how you apply dampers. Okay, the first duct fitting that we're going to look at is the die stamped radius elbow. That first number, the CD3-1, is the reference number out of the ASHRAE guide, so that we could standardize the R divided by D at 1.5. As much as we could, we standardized on that. So it's the radius of the turn divided by the diameter of the duct. And then D is 9.8 inches, which is a really, really strange number. But it turns out that the fittings in the ASHRAE guide were based on metric. And so the 250 millimeter diameter duct was in reality 9.8 inches. So I converted it to English measures so that we could keep everything relative. So the coefficient of loss on this particular fitting is 0.11. The next one that we looked at was the pleated duct. So it still has a radius, it's still round ductwork, and they fabricated it using pleats around the inner radius. This is ASHRAE CD3-5. It uses the same R to D ratio of 1.5. It uses the same diameter. And the C is 0.28. So if you compare that to the first one that we looked at, it's over 2.5 times the losses of the die stamped radius elbow, which if you have a bunch of these, that adds up really quickly. So we're going to look at ones that even get worse than this. They had many gored elbows. I chose the 3-gore 90-degree elbow. They have 4-gore, 5-gore, 6-gore. They're all, in essence, round ducts that are sectionalized. So they have little flattened areas. This falls under the category of ASHRAE CD3-12. It uses the same R to D ratio. It uses the same diameter of 9.8. And the C value, the coefficient of loss, is 0.34. So the losses there are over 3 times the losses of the die stamped elbow. We now look at a mitered elbow. This is for square duct. And they made a point of putting in single thickness vanes. I was sort of surprised by that just in going through this. And I looked at double thickness vanes, or the ones that have little profiles to them. And the losses are considerably higher than they are for single thickness vanes. I'm not quite sure why, but anyway, this is design CR3-9 in the ASHRAE guide. And interestingly enough, it has the same C coefficient of losses of 0.11 as the die stamped that we looked at before. The last elbow is a Z-shaped elbow. It doesn't turn a 90, it turns 2 90s. And what you have to do is keep in mind, if you have 2 90-degree turns that are fairly close together, this is the kind of situation you'll end up with. So this is design CR3-17. The H to W ratio is 2. So the height to the width of the duct itself is 2. And L to W is also 2. L is the distance from the center line of the incoming duct to the center line of the outgoing duct. And so that means that if it's a L to W of 2, that means it's a fairly close Z turn. If the L to W was, say, 10, then it would be in much less losses. But the C on this is 3.76. This is 34 times the losses of the square elbow with single thickness turning vanes. So what you have to keep in mind is you don't want to do this very often, because it really, really, really increases your static pressure within your duct system. Now, this is a really common connection of a round duct coming off a trunk duct. This is ASHRAE ER5-2. These are the ratios that I use, the AS equal AC and the QB divided by QC is 0.5. The Q is the quantity of air in versus the quantity of air out, so about 50%. The C value on this was 1.27. So the losses for this fitting is 11 times the losses of the most efficient turn. So when you have this kind of takeoff to go to a separate branch, you have to keep in mind that there's a lot of losses in this system. Now, so that we don't keep ourselves stuck with all those losses, the smooth Y, which happens to be for a 90-degree, they have smooth Ys for 45 and 30 and 60 and all those other values. But this particular design is an SR5-1 in the ASHRAE guide. And it has the same criteria for the AS equal AC and QB divided by QC is 0.5. Its coefficient of loss is 0.52. So it's considerably more efficient, about 2.5 times as efficient, or 2.5 times more losses than the turn, but it's 150% less than if you just take the 90 off like we looked at previously. Now we're going to get to the dampers. You're going to see why dampers are so detrimental on air distribution systems. This is a parallel blade damper. Its design is CR9-3. The length over the radius is 1.0. At full open, so that the blades are parallel to the airflow, it has a C of 0.52, which really isn't terrible. But if you put the blades at 45 degrees, the C becomes 8.0. So it's 15 times the losses by throttling it 50%. Now that one, the previous one was bad, but the butterfly damper is even worse. The butterfly damper is ASHRAE design CR9-1. It has the same L over W ratio of 1.0. At full open, the C is 0.08. That is parallel to the airflow. At 45 degrees, the C becomes 18.0. So when you're throttling at 50% with a butterfly damper instead of a parallel blade damper, you see the resistance is considerably worse. And the last damper that we looked at was the opposed blade damper, where the blades alternately go left and right. This was designed CR9-5. It's the same L over R ratio. At full open, the C is 0.52. And at 45 degrees, the C is 46. So it really gets bad then on your losses when it's set at 45 degrees. It's not too bad if the blades are parallel to the airflow. Now we're back to, or down to, straight duct pressure losses. The criteria that we used here for all of these examinations would be 1,000 CFM of air. The duct is a standard spiral round duct, and we based it on a 100-foot run. If we start with 10-inch duct, the velocity is 1,833 feet per minute. The losses are 0.522 inches water gauge. This particular design is probably outside the normal envelope of what you would want to design. It's going to be fairly noisy because the high air velocity, and general criteria for duct design is somewhere between 1,000 and 1,500 feet per minute. So this pushes the envelope a little bit, but it gives a point of reference of how much loss you have when you have a 10-inch duct, and then we look at the larger ducts. If we use the same criteria for the air with a 12-inch duct, our velocity drops to 1,273 feet per minute, and the losses drop to 0.209 inches water gauge. So the losses are about half of the losses of the 10-inch duct. So as I mentioned earlier, one of the ways to reduce the static pressure losses in a duct system is to increase the duct size. And to go from a 10-inch duct to a 12-inch duct, we've cut half of the losses, or more than half the losses. This is within the normal design criteria between 1,000 and 1,500 feet per minute. And we're going to lower the noise level some. Now we're looking at a 14-inch duct. The velocity is 935 feet per minute. So now we're down below what the normal design is, but we've cut our losses again by a factor of over 2 because our losses are 0.097 inches water gauge. We're going to have fairly low duct noises here, but we're going to, again, save half of our losses. From the 10-inch duct, we will have reduced this to by more than 5 times. So this is much more efficient. And then finally, we're looking at the 16-inch round duct. The velocity is 716 feet per minute. The losses are 0.49. So again, we've divided the losses by 2. We have very, very low noise levels from the duct. But as it points out, if we go from a 10-inch duct to a 16-inch duct, we've dropped our losses by a factor of 10. So the losses are significantly less. So now we'll look at aspect ratio. The aspect ratio, just in case someone's not familiar, is the width of the duct divided by the height of the duct is the aspect ratio. And for round duct, obviously the aspect ratio is 1 because the width to the height is the same. We put a little chart in here that the perimeter to the area is 1.2 to 1, and we're going to call the relative friction 1.0. So for the same equivalent duct of 40.7 inches round, a square duct would be 3 by 3 feet, has the same aspect ratio of 1.0. The perimeter to the area is 1.3 to 1, so it takes a little bit more material to achieve the same duct cross section. The relative friction is 1.23, so it's 23% more losses in a square duct than it is in a round duct of equivalent area. Next, for those of you who are not familiar with aspect ratio, it is the ratio of the width of the duct to the height of the duct. That gives you an aspect ratio so that you can decide how much losses you have, whether you have a wider duct or a narrower duct. So this little chart sort of synopsizes everything. If you have a 40.7-inch round duct, it has a ratio, obviously an aspect ratio of 1. That perimeter to the area is 1.2 to 1, and the relative friction is 1.0, just as a place to start. For the same duct, it would be 3 by 3 feet square, has the same aspect ratio, but the perimeter to area is 1.3, so you use a little bit more material to achieve the same cross-sectional area. The relative friction is 1.23, so you have 23% more losses due to the little bit larger area and it being square rather than round. If you go to an aspect ratio of 2.25, the duct is 2 feet wide by 4.5 feet, or 2 feet high by 4.5 feet wide. The perimeter to area ratio is 1.5 to 1, and the relative friction is 1.36. So you get 36% more losses if your aspect ratio is 2.25. With a 4.0 aspect ratio, your duct is 1.5 feet high and 6 feet wide. The relative friction is 1.6, so it's 60% more losses. That's about the limit, because you start the materials to make this duct are nearly twice as much material and 60% more losses. Then if you have a 1 by 9 foot duct, aspect ratio is 9. The perimeter to area is 2.2 to 1, and it has a relative friction of 2.23. Okay, as you look at the higher aspect ratios, obviously your losses are much, much higher as you get to the higher aspect ratios, and your materials are much, much more expensive because it just takes more material to get the same cross-sectional area. Maximum practical, as I said, was around 4. Really, anything above 3, your losses are fairly high, and your materials, I mean, they're 50% more materials at the 2.25 aspect ratio. VF drive considerations, since we're talking about taking away VF drives, there's a lot of issues that you have when you have VF drives. You have the harmonic disturbances that we discussed with the 6 pulse versus 12 pulse, having to have harmonic filters. You have active versus passive filters as being 2 of the alternatives. But in addition to the harmonic issues, VF drives, you have to have specially designed motors to prevent bearing erosion, because there's circulating currents that occur that chew up batteries when the VF drives are turned on. So bearing replacements are much higher unless you have some sort of insulation to prevent that. And you can get high voltage peaks, which will damage the motor windings and actually damage the branch circuit conductors if it's a long distance between the motor and the VF drive. There's a way to mitigate that. Again, that's more cost, which is to put inductors between the VF drive and the motor. But we're trying to save money here and not utilize extra construction cost. We're trying to save operating cost, and we've shown that you really can't save the operating cost with VF drives if there's any way to reduce the static pressure in the ductwork.
All right, well, thank you, Ken. Now, thank you for attending the technical session on how to specify motors for more efficient HVAC systems with Ken Laborn. If you have questions, ask them in the discussion forum or ask a question directly to the presenter. This session will also be made available on demand and can be accessed in your dashboard.